All right, so hope you enjoyed the little break, and of course Bjarne's talk. Thanks for the questions. We'll get to more questions later, probably tomorrow. For the people that are watching online, we have your questions. They're excellent. Keep them coming. As I said, we'll prioritize the people in the room since they're actually here, but we try to get to your questions as soon as we can. Right now, we want to move into more of the implementers series. We had the nice designers talk. Sean Parent is a principal scientist at Adobe. It also happens that he was Alex Stepanov's boss for 5 years. Please welcome Sean Parent.
Okay. So Herb and Charles asked me to give this talk, and we went through some negotiations about what I should present. I settled on taking a collection of tips from a mailing list that I post to at Adobe from time to time. I usually call them programming tips, and they're randomly numbered. So every time I send one out, I get a half dozen emails saying, hey, I missed number blank, which is always great. So, but as I started to structure this talk, it was turning more and more into a Scott Myers style talk of effective C++. And I didn't quite want to do that. Not that I have anything against Scott, but he's here, and he should give his own talk. So I started to organize these tips into a set of categories, and I ended up with 3 goals for better code. The wording there is chosen very carefully. So I didn't want to call these guidelines, and I didn't want to call these rules. I wanted them to be goals. These are things that you should strive for in your code that are not always easy to accomplish. And maybe you can't always pull them off. But the closer you come, the better your code will be. So goal number 1, no raw loops. So what do I mean by a raw loop? Well, a raw loop is anything that's inside a function where that function is doing something that's much more than just that loop, right? It's easier to show with an example. I worked at Google for a year, a few years back, and this code is actually from Chromium OS. So you can find this code someplace online. This is an older version of it. It's been improved quite a bit. But I was handed this piece of code for my first code review. Okay, and we can see that this is a method, reposition expanded panels. And we've got this loop in there. Now, if this were the complete function, this wouldn't be too bad. Although even this loop I find to be pretty messy, right? So that's the loop that I'm talking about. We've got a fair number of things going on in there, including erase and insert, which always concerns me when you get operations that have linear complexity stuck inside of a loop. Because now I'm starting to wonder, is this thing, n times n m complexity? Is this a quadratic thing? I don't know. So I've got these checks here that look to be redundant. I've got a comment here that really doesn't tell me what this loop is doing. Okay, so next we're checking, but in the middle of the loop we're doing an erase and an insert. I don't know how that's a check. Okay, but this isn't the whole function, right? If we go down, we'll see we've got another loop. And another one. And another erase and insert here in a conditional. I'm just going to call that out for you. Let's see here. That's failing on me. And if we go down, we've got another loop. Yep, I'm backing up. Sorry, we were going back up there. Okay, we got another loop there, a while loop. We got another loop. This one with a reverse iterator. So let's figure out what that is. And we got another loop down here at the bottom. And that's the end of my function. So that's what I mean by raw loops. Okay? So it's very difficult to reason about a piece of code like that. Now I'm picking on Google a little bit, but I've written code like that. Who in this room has not written code like that? Okay? Yeah. So it's very difficult to reason about a piece of code like that. It's very difficult to prove the postconditions of the loop, and those postconditions that are coming out of the loop are going to affect how you reason about the rest of the function. Okay? Which makes it very error-prone and is likely to fail under non-obvious conditions. What happens if my range is empty? Did I take into account that case? Right? You also start to introduce non-obvious performance problems. It's really easy when you've got a raw loop like that to hide something that has bad complexity, that becomes quadratic, or it's n times m complexity, slows your system down. And it's not just reasoning about the loop, it's everything that happens around the loop that's affected by it. What variables are modified in that loop? How much do I have to understand the body of that loop in order to figure out what this whole function is doing? So, alternatives to raw loops. Use an existing algorithm, right? We've got a bunch in STL. Prefer the standard algorithms if they're available. That just makes it easier for the reader of your code to come along and know what you're doing. People know what sort is. Implement a known algorithm. If it's not in the standard library, go look it up. Okay? You might find it in Knuth. You might find it in any number of good books. And implement it as a general function. And again, somewhat careful wording here. It doesn't have to be a generic function. It doesn't have to be completely generalized. I always tend to write things very concrete the first time, okay, and iterate and figure out how it's general. Contribute it to a library, right? I don't think people do enough of that. One thing that I try to encourage engineers to do, and I have very few takers, but there's a lot of people in this room, make it a goal that every year you'll submit one function or class or small addition to some open source library, okay? Or even an internal library within your company if you can't publish outside, okay? So if you work at a company that does software development like I do, we've got a couple thousand engineers, and we're nothing compared to where Microsoft is at or where Google is at on scale of engineers. Okay, so think about how rich of a library that we could have to draw on if everybody actually did that. Now, if you're not writing any code that's library worthy in a year, then I think you should be rethinking your career. Okay, so everybody should be able to do this. It's also a really good learning experience to go through the process. It means you're taking a piece of work and doing peer review, and even if you fail to get something accepted into a library, you will likely learn a lot in the process of doing it. So, invent a new algorithm. This should happen very rarely. But if you do, write a paper. Give talks. Become famous. Okay? These are all good things. Please don't patent it. Okay? My personal statement. Not my company's opinion, but that's mine. If you want to improve the code quality in your organization, I would say take all your coding guidelines and replace them with the one goal. That's how important I think this one goal is. No raw loops. This will make the biggest change in the code quality within your organization. So I want to give two beautiful examples, because a lot of times when I talk about writing code with no raw loops, people come to me and say, well, I never write algorithms, okay? And I never use algorithms. And I look at their code and it's like, well, you got a bunch of for loops. Oh, but they're simple for loops. Half a page. Okay. A lot of people don't know their algorithms and they don't recognize it. So here's a case. This appears in UIs, probably almost every app you have on your device. You will have a way to create a selection of multiple items. In this case, it's a contiguous selection. Okay? And pick that selection up and drag it to a position, like that. Okay. So think for a minute how you're going to write that piece of code. Okay? Is everybody imagining what this loop is going to look like? Okay. Now, how many people here could do that in one line? Bjarne doesn't count. So nobody? Somebody here? Can you tell me what the one line would be?
Something about slides.
Something about slide.
List slides.
Yeah. Not a splice, but you maybe you could do it with a splice if this were a splice, okay, or if this were a list. But here we've got a vector, right, or some sort of container, okay. So there's an algorithm in STL called rotate that does exactly this permutation. FLP. That's what rotate does. Okay? So, but what if we wanted to go backwards, right? If we wanted to drag a selection from down below up higher, well, that's rotate PFL. Okay? So if we want to take our selection, which is FL, where we start, and we want to move it to any position P, okay, we can determine which rotate to call by checking where P is with respect to the range. Is it before or after? And then calling the appropriate rotate. Okay? Now, we got a hole. We're missing a case. What happens if we want to put things back where they were? Like that. Okay? Well, we don't do anything. So the hole's okay. Okay? But it would be nice if we knew where our stuff landed. Okay? Right? We take our stuff, we move it. Where did the stuff go? We want to know what that final selection is. Okay? So rotate was fixed finally in C++ 11 to return the point, the new rotation point, right? I've got two things that I move around. The new dividing line between those two halves is returned by rotate. Okay? So now I can return, it's new for C++ 11, okay? I can return R there is the result coming back from rotate, right? So I can return the range from either P to R, which would be this case, or it will be R to P in my other case, of where my stuff went. Okay? And in the case where things don't move, I just return where they are. So there's my third case. So I can come up with a good name for this function. We'll call it slide. Okay? And now we can take and we can slide a range F to L to any location P. Okay? Now if you didn't know what rotate did, and you were tasked with dragging things around within a UI and doing this permutation, you would probably write some pretty horrible code. Okay? But what about this case? What if the user can create a disjoint selection? Okay? So they can select multiple items and move all of those guys to some position P. Like that. Okay. Same task. Everybody think about how they would write that. Okay. Anybody know? Okay. That seemed like a hard problem to folks? Yeah? No? Maybe? Okay. So what if I told you that this is actually a simpler case than the other case? Right? Let's break it down. Okay? Let's take just the bottom half. We want to take the selected items and move them to that position. Something we notice here is that when we have these things selected, okay, they will never cross that position line. Okay? I will never end up with items above that. And it's easy to prove because I only have so many items below that, right? I'm taking them up. I'm going to end up with the same number of items, so nothing's going to migrate above. Well, there's an STL algorithm that does exactly this. Right? It's called stable partition. Okay? Stable partition says take the good guys, the selected guys. In this case, we have some predicate S, which is marking our green guys, our selected guys. Okay, and take the selected guys and move them in front and move everything else down, but don't rearrange their relative positions, hence stable, right? An unstable partition would let you shuffle things around within the relative partitions. Okay, so doing this is just a call to stable partition. Okay, well, this half then is just another call to stable partition, but in this case we have to negate our predicate, right? We want the bad guys first and the good guys second. Okay, so we get that. Okay, so we can do the two together and we get this. Now we want to return where did all of our stuff go, just like we did before. Okay, now in this case, stable partition returns what's called the partition point, which is the point between the good guys and the bad guys. Okay, so we've got our two stable partitions returning two locations, so we just make that into a pair and return the pair. Okay, and we can call this function gather. The name was actually suggested to me by Marshall Clough, who stumbled across this working on Eudora, which was an email reader. He works at Qualcomm, and Eudora has a feature where you can hold down some chord key and click on a message within your mailbox, and it will gather all of the messages that are similar to that message right around that. Okay, so exactly the same function. Okay, so how many people are surprised by this? Quite a few. How many people did not know what stable partition was? Most of them. Yeah. Okay. So you have all these algorithms at your disposal, right? Learn them. It's very important. So you'd be surprised at how often the need to rotate thing comes up in real code, right? A lot of times when I'm code reviewing people's code, I'm like, oh, that's a rotate right there. Okay. Rotate is a very common operation. Stable partition is a less common but very useful operation. Okay? Stable sort is another very useful algorithm. Sometimes you don't always want to sort things and have them shuffle around. It drives me nuts when I'm using applications and I go through and I click on the sort columns and it never obeys the previous sort, right? If I want to sort by last name and then by first name, when I sort by first name, I don't want it to randomize all my last names, right? I want it to be sorted first and then last. Stable sort does that. Nth element is another very useful algorithm. I see a lot of people calculating a median of a large set of data. Nth element is a good way to do that. Knowing that nth element also partitions your range is a very useful property of nth element. And you can use nth element then to construct larger algorithms. So let's go back to this piece of code. I just pulled out just the loop from that first piece of code that I showed you. Right? And let's walk through what's going on here. So first, we've got these checks here that seem to be redundant. They are somewhat redundant. And the latter case here, we're deciding between an insert and a pushback, and by determining whether or not we got to the end of our range or not. Well, we can use an insert at the end. So we can simplify this code by just doing that. This conditional that's in the middle of our loop, there's a break statement right after it. So this conditional is only going to execute once. So for now, let's just pull it out of the loop. Okay? So now we've got this check. It turns out that the thing we're searching for in this is always going to be within our sequence. So what the check is here is saying if we get to the end of the sequence, if we're looking at the very last item and we didn't find it, then we're just going to return the very last item. But that's because the very last item has to be the thing we're looking for. So let's not do a redundant check every time around our loop for that. We'll just find it. Okay, so we get rid of that. Now you might recognize this as being a standard algorithm. Okay, that's a find if. Okay, and we can write our little predicate here as a simple lambda function. Okay, so nice use of a C++11 lambda. Okay, so now we've got the body here. So let's look at this. What are we doing? We are taking some item out of our range, storing it, some ref counted pointer thing. Okay, so we're hanging on to ref. Then we're erasing it, and then we're putting it back somewhere else in our sequence. Who knows what that algorithm is? Rotate. That's a rotate. Exactly. It's a very inefficient way to implement a rotate, but that's a rotate. Okay? So we can rewrite it like this. Okay? Now, we've got this test here. Does our panel not equal to our fixed panel? Okay, what we're actually testing for here is the range PF empty, which was a very important test to make when we were doing erases and inserts. Okay? But it's not so important now that we're doing a rotate, because a rotate of an empty range is going to do nothing. Okay? So that's a redundant test. Okay? So now we've got that messy piece of code down to a find if and a rotate. And the code here is considerably more efficient than the previous code that we had. Okay? So if we actually looked at the rest of the function, well, now we can see that the comment that we had was really applying to the find portion, okay, not the rotate portion. But it was really only if we're finding it on the left side, okay? So we're only searching up to our element. And it turns out that everything within that range that we're looking for, we said we're going to find this thing. We've got a less than or equal to comparison here, which maybe you might think implies that this stuff is sorted. Well, if you read the actual function, you would find that yes, in fact, everything except for the item we're looking for is in sorted order. Okay? And we know the item that we're looking for because of f. We just calculated it as f right there. Okay, so we'll just raise that calculation up, and now we can replace the find if with a lower bound, and we can do a binary search for that guy. And if we don't find it, we do a rotate, which doesn't do anything. Okay, so now the code before with the find if was perfectly fine and reasonable and would work. Okay, but now we just took something that was linear complexity and we cut it down to being log n complexity. Okay, so the code gets a bit simpler. Okay, so if we went through the rest of the function, which I'm not going to bore you guys with the tedious nature of that, what we would find is that this rotate here is half of a slide operation. Okay? If you remember back to the slides when I was showing you the code, I called out that there was a conditional insert and erase further down in the code. That's the other half of the slide operation. Okay? So, none of the special cases that were in that loop were necessary. Okay? They all collapse out. So not only did we eliminate the loop, we eliminated all the conditionals. Now we just have straight line code that's very easy to read and very easy to reason about. It's more efficient. Now, okay, it turns out that where this code is used is actually dragging windows within Chromium OS. Okay, you got a list of windows that you can kind of zoom out on, and you can drag a window from one position to another. Okay, so maybe it would be nice if I could command click on a bunch of windows and drag them all to some position. When I have the code that's got a half dozen loops and a bunch of conditionals and a bunch of special cases, and I go to the engineer and say, why don't you support disjoint selections? Their head's going to explode. Okay? It was a very complicated thing. But now that we get it down to a rotate, and then we see, oh, this is really a slide. And if you look at that whole entire function, it's doing three things. It's finding the position P, where things are going for the slide, doing the slide, and then updating the coordinates for all the windows, getting them back into a sorted order. Okay? So that function's doing three things. But once you simplify the function like that, now you can say, instead of just having f here, where you see our range is f to f plus 1 as our selected item, right? If we were using slide, it would be a trivial transformation to say, well, maybe instead of passing f around, we could pass a pair of points and make it contiguous. Or maybe we could just pass a predicate function around and make it discontiguous and replace our slide with a gather. Okay? So, now a little seasoning. Use a range library. Bjarne showed lots of examples of this. It's very trivial to kind of wrap an existing algorithm so you don't have to always say begin and end, which is pretty tedious. Boost has a nice range library in it. ASL, which is the Adobe Source Libraries, also has a range library. So that lets you, instead of saying find begin to end of x, it just becomes find x in A. Okay. Have many variants of the simple algorithms. So find and copy are very simple algorithms that you're going to use a lot. So don't be shy about having, copy bounded, copy with a sentinel, copy n. Okay, so you're going to be doing lots of different kinds of copies. You're going to be doing lots of different kinds of finds, right? So have just a whole collection of them. Look for interface symmetry. What do I mean by this? Well, let's take a look. Here we're sorting a bunch of employees by last name. Okay? So we're using a little lambda function there to get to last name. Now, once my data is sorted, I can use lower bound then to look up an employee. Okay? But look at my comparison function in lower bound. Okay? In lower bound now, I'm comparing an employee against a name, against my string, my last name. Okay? Now, it's really easy when I have these two comparison functions that are closely related, right? I have to be sorting the same way I'm calling lower bounds in order for this to work. It's really easy when they're written subtly different for me to come back and say, well, maybe I want to organize my employees in ascending order instead of descending order. So I'll swap my comparison and sort, and that's going to break my lower bounds. Okay? And I might not see it. So instead, if you pulled out the commonality of those two things, which say really what I've got going on is I've got a projection function that's getting me to the last name. Okay? So then I've just got a comparison function on the last names. So this is a line, this is what I would write using the ASL library, right? I could say sort everything in A by less, okay, by last name. Okay, and the last name there, it's a pointer to a member. Okay, and ASL will just recognize, well, I can turn a pointer into a member into a function where, given an object of that type, I can return the member. Okay, so you can do that with bind, very simply. So now my lower bound, if I also add a projection function, looks the same. Okay, so now I'm sorting by less, looking up employees. I call lower bound by less, looking up the employee last name. So that's what I mean by interface symmetry. Now, range-based for loops, I think, are great, because sometimes you really just want for each, okay, or you want a simple transform, but calling std for each, there is a for each algorithm, or calling std transform for a simple case, sometimes you just end up with more code than you need. So range-based for loops can be very elegant. Some tips here, though. When I'm using a range-based for loop to mean for each, so use a const auto ref for your element. Okay, that's telling me this is not a transform. This is a for each. Okay, if I'm doing a transform, it's going to be a non-const auto-ref on my element. Exactly what I just said. Keep the body short. Okay, the body of the function short. I want to be able to look at it quickly and reason about it, right? If there's a bunch of stuff going on inside of that for each, it becomes a raw loop, right? So my general guideline here is the body should be no longer than a composition of two functions with an operator, right? So f of g of x is okay, f followed by g is okay. So in the case of doing a transform, f plus g is okay. So that's about the extent of the complexity when I say short that I mean. Okay. If the body's longer, go ahead and give it a name. Right? Split it out, give it a name, so that when I'm reading it, I understand what it's doing without having to read all the code and decipher it. Naming things is good. Another tip. Use lambdas for predicates, comparisons, and projections, but also keep them short. So my rules for lambdas is the exact same as the body of a for loop, right? Composition of two functions with an operator is about the extent that I like to see in a lambda. So a lot of times I will see people write these really long comparisons, and it's the same thing that Bjarne put up on the slide for mergeable, right? Right? You can't get mergeable out of a list of 8 Boolean predicates all anded together. Okay? So lambdas are great, but if they're long, use a function, give it a name. We can use function objects with template member functions to simulate polymorphic lambdas. This is something that I believe is getting added for, there's going to be like a less t and greater t in C++ 14, if I've been following the proposals. And you saw earlier, or in my example here, where I just say less paren paren, I didn't have to say less bracket string bracket paren paren. Okay? And the way to do that is, instead of having less be a templated class, less has a templated member function. So here's an example where we write one for last name. Okay, so now I could just say last name paren paren to get an instance of that, and whatever thing I hand to it, it would return x.last for that thing. Where's the less? So in the lower bound expression there, parent comma less.
Yeah, but where is that? How is that implemented? That's not.
Oh, I didn't give the implementation here. So, but the implementation would look much like last name, except it would take two arguments, x and y, and return, x less than y. Okay, goal number 2. No raw synchronization primitives. Well, what do I mean by raw synchronization primitives? I mean mutexes, atomics, semaphores, memory fences. Okay. Why? Because you'll likely get it wrong. Okay? So I say this from painful years of experience. So I'm going to pick on myself here. This is a clip from a copy on write data type, which was a smart pointer type class that I wrote some time ago. It's got an atomic count in there. You can see I highlighted in red all the atomic operations. Okay. There's a race condition between those two statements. Can anybody see it? Somebody here?
You might check that the count is 1, and then you go into the body of the if, but it gets decremented to 0.
It would, if my count is 1, it's not going to end up at 0. No, not quite. Yes, because I'm holding it myself. Want to try again? So for people who couldn't hear that, what he said is when I decrement, or when I check it for 1, then when I do the following statement, it could fall to 0. But it can't because I'm holding on to it. That's what I'm checking for. So if anybody want to try again?
Yeah, the else clause is supposed to be executed if someone else is holding it. By the time you get there, that might not be true anymore.
Right. So, and specifically what happens here, so if somebody else is holding on to this, at the time that I do that first check, then I'm going to fall into the else clause and I'm going to make a copy of my object. Well, while I'm making the copy of the object, somebody else could let go of their reference. At the time that I do my decrement here, I'm not checking to see if I need to let go of the object with that decrement, right? So I'm doing my decrement, somebody else let it, now I've got the only reference. My ref count falls to 0 on that last decrement, but I didn't delete it. Okay, so the fix here is to do that. Okay, now if you didn't have that, then if by chance the reference fell, okay, because somebody else let go of their reference, during that small window there between the first check and the decrement, we would leak an object, right? So in production, what this boiled down to was if you ran the app that this was in for about a week, we would leak 2 to 3 objects. Okay? So it wasn't a serious thing, but it was one of those things that just plagued us. Okay? Where was the leak coming from? Right? Now, the other thing, why no raw synchronization primitives, besides you'll get it wrong, and I've done things like call up Hans Bohm, who did the memory model, and said, is this right? You know? And he looks it over and goes, I don't know. Okay? Right? So here's the model that a lot of people have around threading, is they say, well, I've got this object, right, whatever object I'm working on, and I got a bunch of threads pounding on my object. And so I need mutexes, right, to control all that pounding. Organize things so everybody gets their turn. It's the wrong model to think about threading. Here's why it's the wrong model to think about threading. This is a graph of Amdahl's law. People know what Amdahl's law is? Hopefully everybody knows what Amdahl's law is. Amdahl's law, okay, so as we're reading it here, is basically how well you're going to scale. Okay, so what we've got is performance going up the left, number of processors going across the bottom. Okay, and the line up the middle would be perfect scaling, right? The more processors we add, the better performance we get. Each line that arcs off represents a 10% increment in synchronization. Okay? So you're going to get some amount of synchronization in your app because we deal with shared memory architectures. So every time I do a heap allocation, I'm probably going to get some amount of synchronization there. Right? Right? This is not looking at just locks. These could be atomics, which also are not free. They incur memory barriers and synchronization. Okay? So if I want to build a system that scales, I need to avoid synchronization like the plague. I certainly don't want mutexes in there. No stops. So what's another way to think about threading? Okay. We can think about it from a task model. We can say, well, I've got some task that's doing something, and it's grinding along, and it generates some data. Okay. And I want something to happen to that data asynchronously. So I'll somehow spirit that data over to another task and say, you go grind on that. Okay. And we'll just keep going. Okay. So I need some kind of communication channel between there. Right? Now, a task here, I didn't say threads. Before we had this view of a bunch of threads banging on our object. A task is a little bit finer granularity than that. Okay? It's a unit of work, typically just a function, which is executed asynchronously, and tasks are typically scheduled on thread pools. Right? So we're not completely saturating the machine. So the arguments to the task and the task results then become convenient places to communicate with the tasks. Right? Unfortunately, in C++11, we don't yet have a standard tasking model. Now, I was talking with Herb at dinner last night. He was saying that std async, we're probably not going to change the definition in C++14 to be sitting on top of a tasking model. So, but there hopefully will be a way to get a tasking model in C++14, whether it's async with some option, right, or a new name is yet to be open. Visual C++ 2012 already implements std async on top of a tasking model, though. It's on top of the Windows thread pool. Now, despite the fact that we don't have a standard way, on pretty much any platform that you're likely to be working on, you probably have an option for a good tasking model. If you're on Windows, you've got the Windows thread pool and PPL. If you're on Apple, Apple has their Grand Central Dispatch, also known as libdispatch. And libdispatch is also open sourced, so you can run libdispatch on Linux and Android. And Intel has TBB, which is supported on many platforms. So here's a quickie for you. Just put this on a slide. I'm not going to walk through all the code to understand, but this is a task-based, hopefully C++14 compatible async built on top of libdispatch, right? So if you happen to be working on Mac or iOS and you want the same semantics that you've got on Windows with std async, here's an implementation for you. Okay, so what do we get with the basics if we've just got the async operation there now? Now we can create a task. Our task has some args to another function, which it feeds into that to create a new task. Okay, so async gives us that line of communication. And the two guys go off in parallel, calculating away, and we're all happy until this guy wants the result back. Okay, because then he comes along here and he says get. And what happens? We say, well, let's wait. Okay, let's block this until this guy's done, and then it moves over, and that guy goes away, and now we get our result back. Okay, not horrible, not ideal. So we got two problems there. During the get, we're blocking a thread resource. Okay, so we've got one thread resource tied up. And any subsequent non-dependent operations within our first task there are also blocked. Okay? So unfortunately, C++11 doesn't have any notion of dependent tasks. Makes sense. It doesn't really have any notion of tasks. GCD, which is Apple's solution, has serialized queues and groups that you can use to build dependent tasks. PPL has task chaining, so you've got then clauses that you can use. TBB has flow graphs as another way to slice this problem. All are able to specify dependent tasks, including joins, where two tasks come together. Now, a lot of times, developers think that joins are things that have locks and block. It's not quite the right mental model, right? So let's say that I've got two tasks that are executing, and I want to take the results of those two tasks and use those results combined as the arguments to a third task that I want to get done. Right? Create task 1, it has my result, that drops in. Now my group here has a little counter that gets decremented, right? We're waiting for 2 arguments. Now we're only waiting for 1 argument. Okay. So that task completes, it drops in the other one, and it's that task completing okay, that's decrementing that last count and triggering queuing our dependent task. Okay, so we don't have any mutex where we say, well, we queue this task to a thread and we block immediately and wait until we have 2 results done, right? Pulling on them or spinning on a mutex or something of that nature. Instead, what we do is we say the last guy to finish, trigger the next piece. Okay, so it's a more efficient model. And I'm going to apologize a bit. I tried really hard to get down to something that I could put on one slide as a generalized group mechanism. I couldn't do it. Okay, so it's just, you got 3 separate systems there. They have 3 different models. I could kind of build a common one on top of mutexes, but not in something I could explain in a talk of this length. But I did want to give a couple tips here. Within the standard, we don't have any what would typically be called a thread-safe data structure or a concurrent data structure, something that can be driven from 2 tasks simultaneously. But you do have std_list. Okay? And std_list can be a good tool if you have to, in a pinch, build your own concurrent structure in a fairly simple form by using splice. Okay? So here we've got a lock to hold our mutex, but the only thing we're doing inside of that lock is a splice. Right? If you've got to put in a lock, right, or some form of atomic operation, you want to limit what you're doing in the body of that, right? You want to block for the shortest amount of time possible. So with a list, you can take all the allocations out of it, all the copying of the data out of it, and then just splice things together. So it can be a good crutch. And sometimes I'm working on products where they're like, oh, we don't want to include TBB, or we don't want to include Boost, or we've got this other library that doesn't have a concurrent queue. And I'm like, fine, I will whip one up. Another piece of seasoning, package task. How many people know what package task is in C++ 11 besides the front row? A couple people. Yep. Package task is a great way to marshal results from a task, including the exception, right? It can return through a future both the result of the function as well as rethrowing through that future an exception if an exception happened during the execution of it. It's also a great way you can use package task not just for tasks, but if you want to bridge C++ code with, say, C code that's not exception safe, or Objective-C code, or Lua. Adobe does a lot of programming in Lua, or Java or JavaScript, right? So I actually find that I'm using package task a lot to bridge things together. If you go back when you get the slide deck to my implementation of async sitting on top of libdispatch, I use package task in that implementation to marshal the results, including the exception, back through libdispatch, which is a C function that doesn't know about exceptions. And that brings us to our third rule. The first 2 rules, like I said, the first rule I thought would be the biggest change, would have the biggest effect on your code. The last rule here I expect is the most controversial rule. At least it has been when I talk to people about it. Because when I say no raw pointers, right, I mean a pointer to an object with implied ownership, okay, and reference semantics. So this is a pointer to an object with implied ownership, right? Somebody's got to delete this thing through P. Okay? But this is also a pointer with implied ownership. It's just it's going to go away when unique pointer goes away. And this is also a pointer with implied ownership. Okay? So when I say raw pointers, that includes unique pointers, shared pointers. Now, Bjarne did a great job of teeing this up for me, and you'll see why in a moment here. why do we use pointers to begin with, right, is the first thing to think about. Well, here's a list, not all the reasons, but these are the most common reasons. So we use pointers when things are runtime variable sized, okay, which is sometimes because things are runtime polymorphic, or because they're a container, right? An std vector has a pointer to some block inside of the vector, okay? So that would be a reason why we would use pointers. We use pointers to satisfy the complexity and stability requirements within a container. So list contains far more pointers inside of it, probably heap allocation for every node within the list. And that's to give you certain complexity requirements on how you manipulate a list versus how you manipulate a vector, which would probably be one contiguous block. We use pointers as shared storage when we're communicating with things asynchronously between tasks, right? Futures, message queues, these things are all going to have a shared block within them. We use pointers when we want to optimize copy, right? We might use them through copy deferral mechanism, like copy on write, immutable items. I couldn't come up with a good name for this, but sometimes you have an algorithm that's written in terms of copy, and you really know that it's a permutation. You're only going to have one of each item, so you'd like to convert all your copies to moves. And one way to do that sometimes is to use pointers. And we'll use pointers to separate interface from implementation, right? But for containers, we've already moved largely away from intrusive to non-intrusive STL-style containers, right? How many people here remember coding where to do a linked list, you would inherit from your node class, right? I think there's a couple of us old guys hanging around here. That used to be the norm. You would have these intrusive containers, and every thing within your view hierarchy would probably inherit from some linked list node to build out that view hierarchy. And over time, we've largely gotten rid of that, and we've seen that your code actually gets much simpler if we encapsulate that into this notion of a container that behaves as a regular type, and we can pass it around. Except for hierarchies. And this drives me nuts. A lot of times I see people writing containment hierarchies, right? And they insist that they have to do this intrusively, okay? Instead of just having, each item could just contain a list of the things, or it could contain a vector of things, right? And yet I still see class frameworks and every place where you have hierarchies of views or hierarchies of message dispatchers, people all tend to build those intrusively. But there's no good reason for that other than just nobody's provided a good hierarchy class. Pimple and copy optimizations are pretty easy to wrap up into a class. I'm not even going to bother to show that here. You would, if you think about it for a moment, you'll see what I mean. For asynchronous operations, we already talked, right? We want these channels communicating between tasks, right? Futures are one form of channels that we can use. We can have message queues as another form of channel to communicate between tasks. Okay, so in that case, the shared storage gets packaged up into a higher level construct. So we don't need them there. And that leaves the biggest bugaboo of all, which is, yes?
Solution for this.
For this?
Problem, one-time polymorphism.
Yeah, I got a solution too. Yeah. And that leaves runtime polymorphism. And this is where people tend to get stuck. Right? So let's take a look at an example here. We got a little piece of code here. What we're doing is we've got a document that consists of a vector of objects. In this case, our objects are just integers. And we've got a draw function that can draw our objects and a draw function that can draw our document. Okay? So it's pretty small. It's pretty straightforward. So our client code might look something like this. We can create a document. We can add a bunch of our objects to it, and we can draw our document. And it would output that. But what happens if we want our document to hold any drawable objects? Right? Well, here's the way we would traditionally do it. We would say, oh, we need a base class for our object, which has a virtual draw function, which requires a virtual destructor. And now we've got our document, which is going to be a bunch of shared objects to do our garbage collection for us. Okay? And we can draw our document with all of our objects in it. Okay. So now a client can write their own class that inherits from object and that puts their own class in here. Okay. So there's a bug in this code. Anybody see the bug? It prints, it works. A memory leak? Well, yeah, somebody needs to destroy it. So it's even a little worse, which is in-place back has to make room for where that object goes, and in-place back could throw an exception, and that would leak it. So even if we had something further on in the code that cleaned it up, we could still leak it here. Okay? Now we could fix that by using make shared or something like that. Okay? And we could fix the memory leaks by deleting everything that's in our document. Okay? But there's even a deeper problem, which is we change the semantics of copy, assignment, and equality for our document. Okay? In the original code, if I wanted to copy a document, I would just take a document, create a new document, 2 would go over, I'd get a copy of my document. Now if I create a copy of my document, I get a copy that's sharing pointers with my other one, and I modify one and the copy changes. That's not a copy. Okay? Similar notion, I changed what assignment means. Okay? I changed what it means to compare 2 documents for equality. It used to be that 2 documents were equal if they contained objects that were equal, right? Now, two documents are equal only if they contain the identical objects, which is a different notion. Okay? So this has led to incidental data structures now. I've got these shared pointers around. What do I mean by an incidental data structure? I'll show you in a moment. And also thread safety concerns, right? Now that I'm sharing these objects, so possibly across multiple documents, if I modify one of those objects, it could introduce a race condition with another task that's also working on the same document. So, semantics versus syntax. This is important. We define an operation in terms of the operation semantics, right? Here's a definition of what it means to assign something. Right? When we have shared pointers to an object of some type, each of these components, okay, obeys the regular semantics for copy and assignment, right? I can copy the shared pointer and I can compare a shared pointer for equality, right? And I can assign shared pointers. And each one of those is self-consistent, okay? But that fails to account for the lines, the relationships between these. Okay? So if I think about my shared pointer and the object that it points to as being my one unit, okay? Now, in order to copy that thing, right, I need to copy it needs to be a deep copy, right? I need to copy the thing pointed to it, right? Right? And I really don't have 2 distinct of these things. They're intersecting. So what I've got is this, okay? I've got a data structure, okay, that's being held together in 2 potentially very different places of my code, right? I got some data structure that part of it is in some class over there holding onto it, and part of my data structure is over here. That's what I mean by an incidental data structure. I created some data structure that's just weaving through my code that I can't look at it and reason about. So even though this makes a heart, I don't love these things. Okay? what that does is it breaks our ability to reason locally about the code. And this is the big problem with pointers, and something that Bjarne touched on, right? When I get a pointer back from a function, right, I need to know not just who's responsible for getting rid of it, but am I sharing it with somebody else, right? So I get a pointer back from some class. Do I own it? When do I delete it? If I modify it, does that modify what's in the class? Okay. If it does modify what's in the class, what are the rules that govern that? Who else could be modifying it? What other tasks could be modifying it? Right. So the more I start to refactor my application into tasks and leverage the parallelism that's in the machine, the more complicated reasoning about all these shared pointers becomes. So I say this a lot. A shared pointer is as good as a global variable. And if you think about it, they're effectively the same thing. And yet in code reviews, if you put a global variable in that's modified by two pieces of code, I will guarantee you that the person reviewing your code is going to say, no, globals, you shouldn't do that. There are rules. But if you put a shared pointer in, they're going to say, oh, good. You're making sure that somebody's deleting that. But it's the same thing. I have two pieces of code banging on the same piece of memory. So how else could we do this? Okay. So here I rewrote my object. Okay. Now this is a bit more complicated. But what I'm doing is in the middle there you'll see the concept T, which is basically my base class. Okay. It's pretty much identical to the base class I had up there for object before. But now, instead of that being the interface to my thing, okay, what I'm saying is you just pass in anything that's going to satisfy the requirement of being drawable, okay, and I will construct the instance of the subclass inside of this. And if you'll see in the bottom, I've got a shared pointer, but it's a const shared pointer, okay. And const shared pointers I object to much less because they have the same value semantics, okay. So now I can't, if it's a const shared pointer, I can't have two tasks modifying the same object. I'm protected from things like that. I can't have two pieces of code modifying the same object. So my shared pointer here is just an optimization of copy. Okay? I don't have to copy these things because they're not mutable. Now, an interesting observation is that when you have polymorphism, I'm not convinced that mutability is ever a requirement. Okay? So if you wanted mutability in something like this, there's a few things that we could do. We could actually make copies, in which case the code would get a bit longer. Or we could make a copy on write here if we wanted to by checking to see if our shared pointer is uniquely owned or not. Okay, but if you think about it, if I've got some class and it's got some operation on it, and the operation is not a const operation, it's something that's setting a property of it, then the odds are I only have one representation of what that property is. It's trivial to construct counterexamples where I could say, well, I want some polymorphic sequence, which is either going to be a vector or a linked list. But in practice, that isn't particularly usable because now my polymorphic object has the requirements of that thing for the complexity requirements are some mix between a vector and a linked list, right? You're probably better off just making the decision and saying at the top, I will have a vector or a linked list. So I've yet to be convinced that in practice mutability is a requirement. Now here's how we go ahead and we just have back to our vector of objects. And we go back to the old draw function that just draws our objects, right? So now we can write a piece of code that looks like this, where we create our class, and it's got a draw function, and we put it back, and just as in Bjarne's example with the, I think he called them gadgets, right? I don't have to new my object, okay? So this has other nice side effects now. I'm separating the requirement of polymorphism to the place where I'm using the polymorphism in the document. And if you see here, my class doesn't inherit from anything, right? It's no longer entangled, okay, with the notion of my document through inheritance. So that's a really nice feature. That means I don't need multiple inheritance, and I don't need multiple virtual inheritance, okay? And I don't need diamond of death class hierarchies, right? If I want to use my class in some other polymorphic setting, it just has to satisfy the requirements for that other polymorphic setting. Okay? So a couple of tips here. We can use make shared when we are using shared pointers to eliminate an extra heap allocation, right? Make shared is a little more than a convenience routine. You have to have, if you've got a shared pointer, there has to be a ref count somewhere. And typically, if you just construct a shared pointer with a pointer, then it's got to heap allocate that ref count. Okay? If you use make shared, it puts those two into one object. So we can pass sync arguments by value and move them into place. So an example is just the one up above there. When I'm constructing my object, it's taking an argument t by value. What I mean by a sync argument is an argument that's going to be stored. Okay? In this case, we're storing it inside the class or returned. Okay? So with C++11, about the only place you need R-value references is constructors, assignment operators, and that's only because of a language defect. Okay? And that's pretty much it. Okay? So the only place you really need to use move is when you're syncing something, when I need to carry that sunk argument down to its final location. Right? I don't need to use move returning from a function. That's now returning a result from a function is defined in terms of move. So, some nice tips there. Come to my inheritance as the base class of evil talk, which is a 20-minute talk, and it's going to be a blazingly fast talk on Friday. And we'll talk more just about evils of inheritance and better ways to do polymorphism. A recap. These are the 3 goals that I covered. And really what this is all about is locality of reasoning, right? When I pick up a piece of code and I'm reading that piece of code, ideally everything that I need to know is in that piece of code. And I don't have to go and look at my entire system in order to reason about just a snippet, right? I don't have to know what other classes are banging on my objects, right? If I achieve that, my code gets more composable, it gets more general, it's more correct, it's more efficient. Add all the little adjectives you would like there, more secure. Okay, and that is the end of my talk, and I've got a few minutes for Q&A, if anybody has questions. I can see I've got one question up here, but probably house lights would be good.
Yep.
In the no raw pointers pattern, the object T and the model inside it, it seems like most of the value comes from using a shared pointer and the fact that the representation is read-only.
So,
is there any particular reason why simply using a shared pointer to const as your top-level value would not work as well and save you the trouble of inventing a base class or a wrapper?
typically, I wrote that because it's the shortest form of that pattern that I can write for one slide. Typically, I actually don't use a shared pointer in there. I use a unique pointer, and I implement copy. So the top gets a copy constructor, which then gets virtualized through a copy method on the model. If you want to see an example of that, come to my talk on Friday. It's just about half a page more code, so I didn't want to go through it here. Okay.
Got it.
Yep.
If you go back to the 56th slide, you have a list splice
Yes.
going on. I'm curious if your standard library implementation is I mean, as far as I'm aware, C++11 requires that splice be linear time. And if that's true, then would you still recommend doing that, or would you recommend using vector or something else instead?
I wouldn't recommend using vector in this particular case, which if you were doing an insert in the middle, well, the problem is you have to lock the vector potentially through a reallocation as the thing grows. The splice here is actually guaranteed to be constant time. The standard doesn't guarantee that all splices are guaranteed to be constant time. There's a trade-off for people who don't know between guaranteeing that splice is constant time and guaranteeing that size is constant time. And the standard decided with C++11 that they're going to guarantee std size is constant time, which means that there's one case where splice is not constant time. And that's basically where I'm splicing from the middle of a list into another list. Here, I'm splicing an entire list, so size can still be implemented in constant time, and there's no conflict. Any other questions?
No, not
See
Somebody
it?
down here?
It's me.
With passing your sync arguments by value,
Yes.
large objects that adds an extra move. So that the compiler cannot remove, because if it's user defined, the compiler cannot remove.
Right. So it adds the thing here is it adds an extra move that the compiler cannot remove. Yes, you can get this is passing sync arguments by value. You can take the approach where you would write two forms of the operation, one that's copy, taking a const reference, and one that's taking an R value reference. My objection to that is that those cases that matter are actually very rare, because typically when you have a large object, the large part is heap allocated and the move doesn't cost you anything because it's just moving a pointer. And the problem with doing the two forms of the function is it's a permutation problem. You have to do this for every sync argument. And a lot of times in a constructor, you don't just take one value that's a sync argument. I might have 3 or 4 values in my constructors that are sync arguments. And this is where it comes up a lot, in which case now I have to do all permutations of copy and move for all 4 of those arguments.
So
And your
instead
code
you
space
use
goes up.
uref and forward, and enable if to make sure the types are the right type.
Right, which in my opinion you can do, and it's a fair amount of complexity to do. I try to keep things as simple as possible. So I give another talk on why performance of C++ doesn't matter, which is not what you think, but a whole different talk.
So we do have one from online, which,
Sure.
do you want that?
Yeah, absolutely.
Okay. So this is more of a general question. Where can you find more information about removing raw loops? So more learning materials besides your excellent talk. And he says, ideally, it would consist of problem statement, unit test, and sample loopy solution. So basically, more information where?
More information where? Boy, that's a good question. I don't know. The first thing that I would do is learn your algorithms. Right. If you can't recognize that something is an existing algorithm if you don't know your algorithms to begin with, right? If you don't know what all the standard algorithms are and what they do, you really should. You've got this incredibly powerful toolbox there. Okay, so that would be where I would start. If somebody in the front row wants to write a book, maybe this would be a good book.
Actually, Sean, while we were listening to your talk, Scott already decided that you need to write a short book showing exactly these examples. Please do that.
Thank you.
Yeah. All right. I think it's 12:15. The lights just went down for some reason. I guess no reason. One more question, anyone? We have one right over here. Okay, I'll go give it to you. Well, you can give it to him. See him? Raise the hand.
Yep. 5. On that last slide, I just had a small question.
last slide.
The one that had the pushback, the synchronized there.
Oh, yeah.
Why is it preferable to write the code that way and not to just do a pushback underneath the lock
Not
guard?
just do a pushback, because if I do the pushback underneath the lock part, then I'm going to get a heap allocation for that node inside the lock, okay, which is going to be a longer operation than the splice. So I'm going to be blocking for more time, right? So if I have multiple threads who are using this concurrent queue, it's going to greatly increase the amount of synchronization that I have going on.
You'll also invalidate if you have
What's that?
vectors.
You'll also invalidate if you use a vector and other threads who have pushbacked and then obtained a reference to the item will not be happy. The
Yes.
list doesn't do that. So
Yes, and I didn't show what DQ looks like. And there's an interesting thing here. If you actually put the entire implementation up here, there's another piece missing, which is usually a useful piece of information for a concurrent queue that very few concurrent queues have, is did the queue go dry? And what I mean by that is did somebody try to dequeue an item and there was nothing in the queue to get? Okay, so typically that's a very useful piece of information because you're using concurrent queues to string tasks together, and when the queue has gone dry, then you want to queue the next task. Okay, so normally actually my enqueue would return a bool, which is did this queue go dry? Okay, which has to be communicated between the DQ and the NQ side. You can't determine whether or not the queue's gone dry from the NQ side. So just another tidbit if you guys actually want to implement something like this. And my clock stopped, so I could go on forever. I've forever got 1 minute and 16 seconds. Yeah, I think we're done.
Thank you.
Wrap it up.